Hi, today we are going to discuss about CMOS logic arrangements. So, I am going to discuss about the other forms of CMOS logic in this video. So, the other forms of CMOS logics are pseudo NMOS logic. If you see here, this is a pseudo NMOS logic and the circuit shown here is a pseudo NMOS NAND gate. Okay. So what is going to be happen for this circuit? So here the PMOS is directly connected to ground potential here. What I did here is this PMOS is directly connected to ground potential. So when it is connected to ground potential due to bubble, it will complement the ground potential to logic 1. So I repeat here, when I am giving a ground potential of 0 volts at the input of PMOS, it will complement the logic 0. So it will complement the logic 0 means it will be at logic 1. Definitely these PMOS will be turned on always. So at always at real time or at always this PMOS will be in turned on state itself, due to because this PMOS is directly connected to ground potential here. So that's the reason. So the same thing as written here, the CMOS pull-up network is replaced by a PMOS transistor with its gate grounded. So same thing I did here. This gate is connected to ground potential. So that's the reason gate is connected to ground potential. Definitely it will be turned on in during the real time itself. So it will be always turned on itself. So that's the reason, since the PMOS is not driven by any signals and it will be always turned on. The same thing I've written here. Next, therefore the effective gate voltage seen by the PMOS is VDD. So thus the over voltage on the P gate is always VDD minus V threshold point of P channel. So that has written in the point number 2. So when the NMOS is turned on, means whenever I am giving a input voltage here. So the point here, third point here I am discussing is when the NMOS is turned on. So when the NMOS is turned on, whenever I am giving an input to this N channel, definitely it will be turned on. So that was I am discussing. So when the NMOS is turned on here, so there will be a direct path between VDD to VSS, right? So when I am giving one input here, A, B, C is equal to 1, these three transistors will be turned on. So it makes a low resistance path between VDD to VSS. So a direct path between supply to ground exists and static power will be drawn. So the total static power will draw. So however the dynamic power is also going to reduce here. So from this pseudo NMOS logic. So if you go in overview of this pseudo NMOS logic, so this is a resultant waveform between V input as well as V output. So this is all about the overview of this pseudo NMOS logic. So we are going to study about the characteristics between V input as well as V out here. So now I am going to sweep the input voltage from ground potential to VDD here. I am going to sweep the input voltage from ground potential to VDD. Sweeping means I am going to change the input voltage from 0 level to VDD. At some steps I am going to change the voltage from ground potential to VDD here. So we encounter some from regions of operations. These are the some regions of operations here. So under the voltage, this is all about input voltage only. So whatever that I am representing in red color are all are input voltages. So when the input voltage is between 0 to V threshold voltage of N channel. So I repeat, at the first step, when the voltage is between 0 to V threshold voltage of N channel, so it is between VSS to VTN, the T1 will be off and T2 will be linear. T1 off means NMOS will be off. This NMOS will be off when the voltage is between 0 to V threshold voltage of NMOS. So if it is between 0 to VTN, this NMOS will be turned on and this will be in linear mode. So that is I am saying here. So in going to the region 2, so when the voltage is between VTN to VDD by 2. So see, observe carefully here, it exceeds the voltage of V threshold voltage of N channel here. See, observe carefully here, the threshold voltage of N channel exceeded. So definitely it will be activated. This N channel is going to activate. So that's the reason this NMOS will goes to saturation and PMOS will be in linear itself. So when it is between VTN to VDD by 2, which we have already studied all these cases in our previous videos also. Right. Next, when the voltage is between VDD by 2. So see here, the intersection point between input and output is VDD by 2. Here VDD by 2 in case of input, and here also VDD by 2. See, observe carefully. So if you draw a line perpendicular to this in input VDD by 2, definitely I am going to get a VDD by 2 at the output itself. So under the VDD by 2, NMOS will be in saturation and PMOS will be in also saturation mode, right? And next, in going to the region 4, when it exceeds the voltage VDD by 2 to VDD minus V threshold point of P channel, so between these two voltages, the NMOS will move from saturation level to linear level. It will move from saturation to linear, and PMOS will be in saturation itself. So between the point VDD by 2 to VDD minus V threshold point of P channel. So in the last case, VDD minus V threshold point 2 to VDD. So between these 2 points, so between these 2 voltages, the NMOS will be in linear and PMOS also will be in saturation itself. So simply it is acting as inverter, no need to worry here. So if you see here, if the input voltage is 0, the output is VDD here. If the input voltage is VDD, the output voltage is 0. So simply it is inverting the action from 0 level to 1 level or 1 to 0 level. I repeat, when input is 0 here, this x-axis represents input and y-axis represents the output. So if you observe here, if 0 is there, for 0 input the output is VDD. For the 1 input the output is 0 here, right? And next, in going to the realization part of this pseudo NMOS inverter driven by another similar pseudo NMOS inverter. So if you see here, this is pseudo NMOS inverter, this is also pseudo NMOS inverter. So no need to worry here or no need to confuse. Here the PMOS gate is connected to ground. The same thing I did here. This PMOS is connected to ground potential and this PMOS is directly connected to ground potential. I repeat, PMOS is connected to ground potential and this PMOS is also connected to ground potential. So now I am going to realize the required ratio, nothing but Z pull up to Z pull down ratio. So that will be going to exist when it is at the point of saturation. Okay, where we are going to find out that Z pull up to pull down ratio is when it is going to reach approximately to the value of VDD by 2. So that has been written here. So when the V inverting input is reaching at the point of VDD by 2, nothing but when it is going to reach at the saturation point, we have to calculate Z pull up to Z pull down ratio. So by applying some appropriated values in the saturation equation, IDS is equal to K into W by L into VGS minus VT whole square by 2. So that is our formula, we have already known and we discussed that saturation voltage IDS is equal to K into W by L into VGS minus VT whole square by 2. So by substituting these typical values, these are all typical values which we have studied in our VDS versus IDS relation. The same thing I am going to repeat here. What I am doing here is, in order to determine the ratio, we have to consider some conditions for which the V inverting voltage should be approximate to the value of VDD by 2. That should be approximately equal to the value of VDD by 2. So when it is approximately to the VDD by 2, so it will be in the saturation itself. So the NMOS will be in saturation and the PMOS will be in resistive region. So what happens? So it will be in saturation means formula is there. Our formula IDS VDS relationship, we derived some formula for the saturation level. So what that formula, IDS is equal to K into W by L into VGS minus VT whole square by 2. So by substitute that values here, this V inverting voltage, threshold voltage, VDD voltage, all voltages, if you substitute, we will get the Z pull up to Z pull down ratio of 3:1 here. So from the pseudo NMOS logic, we reduced that Z pull up to Z pull down ratio for an inverter followed by an inverter 4:1 to 3:1 here. So that is the advantage of this other form of pseudo NMOS logic. Next, in going to the dynamic CMOS logic. So this is our dynamic CMOS logic. So dynamic means which is going to vary with respect to the time. So it requires some clock, definitely. I repeat, in going to the dynamic CMOS logic, dynamic means it is going to vary with respect to the time. Am I right? So time means a clock pulse is required here. So that's the reason the clock pi is given to both the gate inputs of PMOS as well as NMOS here. Right? So the actual logic is implemented in inherently faster NMOS logic. This is inherently NMOS logic, nothing but N block. A P transistor is used for the non-time. This P transistor is used for non-time critical precharging of the output line Z. So it is used for precharging. So precharging the output line Z. Okay, so that if there is output capacitance here, so that the output capacitance is charged to VDD when the clock pulse is at off period. Don't get confused, I repeat here. So here one point I have written here, during the off period of clock pulse. During the off period of clock pulse. Off period of clock pulse means when pi is equal to 0. So when I am going to give a 0 here, what happens? It will be cut off. So it will be cut off. This NMOS will be cut off. I repeat, during the off period. I repeat, during the off period. So pi is equal to 0. This NMOS will be cut off and PMOS will be, what happens to this PMOS? So 0, bubble is there, it will complement and it will be turned on. This PMOS will be turned on. So under the off period it will be turned on. Therefore definitely this VDD will drop across this output line Z. So if I place a capacitor here, this capacitor will charge. Is it clear to you? I repeat, if during the off period of clock pulse, so when the pi is equal to 0 here, it will be turned off, it will be turned on. Therefore this VDD is going to exist at the point Z with respect to the ground. If I place a capacitor here, it will charge, and this total process is considered as pre-charging phase. So this total process is considered as a pre-charging phase. Okay, and during the same phase when the clock is on. So when the clock is on, now I am going to discuss about the clock on. When it is on means pi is equal to 1, this N transistor will be turned on and it will be turned off. Why? Because I am going to give a 1 here, the 1 is going to exist here. So here bubble is there, so 1 bubble is there means it is going to complement, so 1 will convert into 0, so this PMOS will be turned off. I repeat, when the clock pulse is on or during the on period of time, on period of time means pi is equal to 1, 1 is given to NMOS as well as 1 is given to this PMOS. So due to bubble at the input, this PMOS will be complement the input, so 1 will become 0, so this PMOS will be turned off and therefore this NMOS will be and therefore this NMOS will be turned on, it will be turned on. So turned on means this total process is considered as evaluated phase. So during this dynamic CMOS phase, we studied about pre-charging phase as well as evaluated phase. So pre-charging phase is when the clock pulse is 0 and evaluated phase is when the clock pulse is 1. So that has been written in the next slide. So this is all about simple single phase dynamic CMOS. So this is our simple single phase dynamic CMOS logic. So I simply written 2 points here, that is the description of this total circuit. So pre-charge period means when clock pi is equal to 0, evaluation period is when pi is equal to 1. So in going to the drawback, so inputs can only change during the pre-charge period. The inputs can change only during the pre-charge period. Pre-charge period means when pi is equal to 0. So we can change only during the pre-charge period, not in evaluation period. When you change in evaluation period, definitely the output will be a corrupted one. When I am going to change the input at evaluation period, the output will be a corrupted one. So that is the main drawback of this dynamic CMOS logic, right? In going to the CMOS domino logic. So CMOS domino logic is a modified version of this dynamic CMOS logic. So simply the modified version of this dynamic CMOS logic is our CMOS domino logic. So additionally one inverter is added over here, that's it. So an inverter is added at the output. So it has similarly like our dynamic CMOS logic, it has pre-charge phase as well as evaluated phase. When clock pi is equal to 0, pre-charge period. When pi is equal to 1, it is an evaluation period or evaluation phase period. Next, in going to the clocked CMOS or C square MOS logic. So this is, so here 2 clocks are going to be used. So C square, 2 clocks are going to be used. 2 clocks are going to be used here. One is normal clock and second one is the complementing clock. See here, this is the resultant circuit of C square MOS logic of 2 input NOR gate, and this is an inverter, right? So this is a C square MOS logic of, this is a C square MOS logic of 2 input NOR gate, and this is a C square logic of 2 input inverter. So this is a 1 input inverter, this is 2 input NOR gate C square MOS logic, and this is an inverter of C square MOS logic. So if you observe here, it is having two clocks, one is the normal clock and another is a complementing one. See here also pi is there, pi bar is there, pi is there, pi bar is there, pi is there, pi bar is there, pi is there, pi bar is there. So two clocks are there here. So if you go to our dynamic, only one clock. In going to this domino also, there is only, in case of domino also it is having only one clock, but here there are two clocks, pi as well as pi bar, right? So this logic is implemented both in n channel and p channel transistors in the form of pull up p block as well as complementary n block pull down structure. So this is pull up and this is pull down, what I am saying with this statement. So if you see a figure A, this is an inverter based CMOS logic which we have discussed earlier, this one only, right? So however, the logic in this case is evaluated during only on period of the clock. Simply we discuss it here now, evaluation period as well as pre-charging period. The same thing here also. So however, the logic in the case of evaluated, so evaluated means connected to the output. Evaluated means connected at the output, nothing but. So here 0 at the input, pi is equal to 0 means pre-charging period. When pi is equal to 1, it is an evaluated phase. So same thing here also. However, the logic in this case is evaluated only the, evaluated means connecting to the output. So only during the on period of the clock. Okay, as might be expected, a clock inverter circuit is there. So clock inverter circuit forms a part of this family as a logic, which we also been shown in the figure B, which is inverter. So with what I am saying here is, it is having a additional clock which is nothing but a clocked inverter circuit, pi bar as well as pi bar here. So simply it is doing a pre-charging period as well as evaluation period, which we have discussed in dynamic as well as in domino logic. The same thing is going to be happen, no need to worry. But here it is having two clock pulses. So one is pi and another one is pi bar. So to reduce the drawback which we have seen here, why? Because the corrupted output will occur. So to reduce, the remedy for this is this one, see, a clocked CMOS logic. However, the logic in this case is evaluated only during the on period of the clock. As might be expected, a clock inverter circuit forms a part of this family as shown in the figure here. Owing to the extra transistor in series with the output, it will rise to a slow rise time and fall time that can be expected, right? So all these logics are about a pre-charging period as well as evaluation period itself. So simply it is also making as an inverter action. Okay, during the pre-charging period means it is charging. So when we are giving input pi is equal to 0 here, pre-charging means it will goes to logic 1. So when we are giving logic 1 to this NMOS circuit, so the output will evaluate it. So output evaluation means it will reaches from 1 to 0 state, discharging of the capacitor, right? In going to the last one, NP CMOS logic, which is nothing but zipper logic. What I am going to do here is, I am going to arrange the circuits, arranging the N blocks as well as P blocks alternatively here. So N block here, P block, N block. Definitely in the next state it will be P block. So alternatively I am going to connect the MOS block circuits. So here the pre-charge and evaluation transistor fed from the clock and clock bar alternatively, and clearly the function of the top and bottom transistors are alternative between pre-charge and evaluation. So as I said in the previous session also, here evaluation period and pre-charge period, here is there pre-charge evaluation, here also pre-charge evaluation, pre-charge evaluation, pre-charge evaluation, here also pre-charge evaluation. The top and bottom transistors also alternate between pre-charge as well as evaluation period. But what about the zipper logic means, this is also called as zipper logic, where we are going to connect the MOS transistors alternatively, the blocks of MOS transistors alternatively, N block followed by P block, P block followed by N block itself. So this is all about the different forms or other forms of CMOS logic. Okay, in the next class we will discuss about the designing of multiplexer using MOS circuits. Okay, for reference go through the textbook Basic VLSI Design by Douglas A. Pucknell and Kamran Ishragian. Thank you very much.